Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR, Enterprise Core exam. This course will cover all topics you need to know to pass the ENCOR exam. In this video, we will look at Traceroute, a useful tool for troubleshooting network reachability. Traceroute, as the name implies, allows you to trace the route to the destination. In the lab video, we'll use Traceroute to do some troubleshooting. But in this video, we'll see how it works first. Here's what we'll cover. First, I'll introduce what Traceroute is and how it works. Then, we'll look at Traceroute on two different platforms, Windows and Cisco IOS. They work a bit differently. Finally, I'll explain a limitation of Traceroute, because although it is useful, it's not always a perfect tool. Let's get started by looking at Traceroute in general. Traceroute is a tool used to trace the path from source to destination. This can be used to confirm if traffic is taking the intended path through the network. Also, if a destination is unreachable, Traceroute can be used to discover how far traffic can travel before it is dropped. This is useful for troubleshooting. It can help identify which router in the path is causing problems. Traceroute works by sending packets with a TTL of 1, then 2, then 3, etc., until reaching the final destination. And each router in the path sends ICMP time exceeded messages back to the source. Those are ICMP type 11, code 0. As I mentioned in the ICMP video, before a router forwards a packet, it decrements the packet's TTL by 1. And if this would result in a TTL of 0, the router will discard the packet. It will not forward it. Then it will, of course, send a time exceeded message back to the packet source. So let's see how that works when PC1 sends a traceroute to PC3. First, PC1 sends a packet to PC3 with TTL1. R1 drops it and sends a time exceeded message to PC1. So when PC1 sends the message, the TTL is 1. If R1 were to forward the message, it would have to decrement the TTL to 0, so instead it drops it and sends the time exceeded message. Then, PC1 sends a packet with TTL2. This time it reaches R2, which drops it and sends a time exceeded message to PC1. Then PC1 sends a packet with TTL3, and it reaches R3 before being dropped. Finally, PC1 sends a packet to PC3 with TTL4, and it reaches PC3. PC3 sends a message back to PC1. However, the kind of message sent back by PC3 depends on the kind of message sent by PC1. It varies by OS. As I'll show later, in Windows, Traceroute uses ICMP echo request messages. But in Cisco IOS, Linux, and macOS, it sends UDP segments. Let's look at the output here on PC1. Note that it is a Linux host. So the command is traceroute, followed by the hostname or IP address. Now let's look at the output line by line. First, here's R1's response. Note that it shows the hostname, r1.jeremysitlab.com, then the IP address, and then 3 responses from R1, each showing the round-trip time, the time it took from PC1 to R1 and back. So that means that PC1 actually sent 3 messages with TTL1, not just 1, and PC1 received 3 time exceeded messages from R1. And how does PC1 know the hostname of the hop? In this case, I manually configured the hosts file on PC1, so it would show this output. But if DNS is configured, it will ask its DNS server if it knows the hostname associated with each IP address. PC1 then sent 3 messages with TTL2, and got 3 responses from R2. Then TTL3, and got 3 responses from R3. Finally, it sent 3 messages with TTL4, which managed to reach PC3, so it got 3 responses from PC3. Remember that Traceroute sends 3 messages with each TTL value by default. This is true on Linux, Windows, macOS, Cisco IOS, and probably others too. Okay, so those are the basics of Traceroute. Next, we'll look at a few details, but Traceroute generally works the same, no matter which platform you're using. Now let's look at Traceroute in Windows. There's not much to point out, just a couple things. In Windows, the traceRT tool is used to perform a traceroute, and that's the command in the CLI, traceRT. Unlike in other platforms, it sends ICMP echo request messages. Basically, it just sends pings with specific TTLs. So, each router in the path will send time exceeded messages, and the final destination will send echo reply messages. Here's the command in the CLI, traceRT, then the destination IP. In this case, I also added -d. This is optional. It tells the PC to not attempt to resolve the IP addresses to host names. If you want your computer to try to resolve the IP addresses, you don't need the -d. But if you don't need that info, it makes the traceroute much faster. The traceroute command can take a long time, but this makes it faster. So, here's the output of the command. As I said in the previous slide, the PC sent 3 messages with each TTL. So, 3 echo requests with TTL1, 3 with TTL2, etc. Finally, the requests with TTL8 reached the destination. Here's a packet capture of that traceroute. I'm not showing all of the messages here, just the last few hops. Here are some ICMP echo request and time exceeded message pairs. And then at the end, it's ICMP echo and reply. Here you can see more details. This top echo request is the last one with TTL5, as written on the right of the top message, TTL equals 5. And here are 3 echo requests with TTL6, and 3 time exceeded messages in response. Then the same for TTL7. Finally, with a TTL of 8, the echo requests reached the destination and got their echo replies. So that's traceroute in Windows. The main points are that the command is traceRT in Windows, and that it uses ICMP echo request messages, unlike Cisco IOS and other platforms, which send UDP segments. Now let's move on to traceroute in Cisco IOS. In Cisco IOS, the traceroute command sends a series of UDP segments with no encapsulated data. The destination port of the first segment will be 33434, then 33435, 33436, etc. And as on other systems, by default 3 segments are sent per TTL. Each router in the path will send time exceeded messages, and the final destination will send destination unreachable messages, specifically with code 3 for port unreachable. Why port unreachable? Well, it's because 33434, 33435, etc. are not significant port numbers that might be used by an application on the device. So the device will send port unreachable messages to say, I'm not running any applications on this port. So this time from R1, I sent a traceroute to PC3. Note that it automatically converted the IP addresses to host names. That's useful when you can get that information. However, as I said before, it can make the command take a long time, especially when it can't resolve the host names immediately. So you might want to add numeric to the end of the command to speed it up. You can use numeric to prevent the router from resolving the IP addresses to host names, like adding -d to the command in Windows. Here's a packet capture of that traceroute from R1 to PC3. These top messages are the UDP and ICMP time exceeded messages, and the bottom 3 UDP segments receive port unreachable messages from PC3. Look at the port numbers. As I mentioned in the previous slide, the destination port starts at 33434 and then increases with each message. And when the UDP segments finally reach the destination, PC3, R1 receives port unreachable messages, ICMP type 3, code 3. In the MTU video, I showed how to do an extended ping by simply using the ping command with no destination. You can do the same with traceroute. I generally accepted the defaults, but highlighted a few things I specified. For example, I specified numeric display, so it doesn't show the host names. I also set the probe count to 10, so it will send 10 messages at each TTL. And here is the output. Notice as I've highlighted, it missed one reply from PC3. That's the asterisk. I guess R1 was sending messages too fast, and it surpassed PC3's rate limit for sending ICMP unreachable messages, so R1 didn't get a reply for that one. This is a chart from Cisco that indicates the various output codes that you can receive in a traceroute. If it's successful, you should see the first one, the number of milliseconds for the round-trip time. The others indicate some kind of error. Notice that port unreachable, with a symbol of U, is listed as an error. Keep in mind that doesn't apply to the final destination, from which R1 expects to receive port unreachable messages. I don't think you need to memorize these, and for some of them, I'm not sure if or when you would actually get them in a traceroute. I'm just showing this chart for reference. Finally, let's look at an interesting limitation of traceroute. There are other limitations. For example, some devices will simply refuse to send ICMP unreachable messages, or a firewall might block them. But we'll just look at one limitation. Depending on how devices in the path load balance traffic, traceroute could give inaccurate results. For example, I used the following command on PC1, a Linux host. The -n means to not resolve the addresses to names, and -q1 means to just send a single probe per TTL, instead of the default 3. So the first response comes from R1, of course. Then R2's G00 interface. Then R5's G00 interface. Okay, that's odd. It looks like the traffic jumped from R2 to R5. And the next response is from R6 G00. So it looks like the path jumps between the top and bottom paths. The reason for this is that R1 is load balancing the packets over the two paths. The TTL2 message was sent to R2. The TTL3 message was sent to R5 via R3. And the TTL4 message was sent to R6 via R2 and R4. Now, what if I did it with the default 3 probes instead of 1? Let's see. The first hop is just R1, of course. The second hop is jumping between R2 and R3. The third hop is jumping between R4 and R5. And the fourth hop between R6 G00 and G01. To demonstrate this issue, I set R1 to do per packet load sharing, with the IP load sharing per packet command that I showed in the Ceph video. That's not the default. However, in a real network, you might not have control over how devices in the path load balance traffic, so you might get unexpected results. Here's what we covered in this video. I briefly introduced Traceroute, and we looked at how it works in Windows and Cisco IOS. Windows devices use ICMP echo request messages, and Cisco IOS and other operating systems use UDP segments. Finally, we looked at an interesting limitation that might cause Traceroute to give inaccurate results. Okay, now let's move on to the quiz. Here's question 1. Examine the following output from a packet capture of a traceroute. What kind of device is the host at 192.168.1.224? Pause the video now to think about the answer. Okay, the answer is B, Windows. We can know that because the device is sending ICMP echo requests to do a traceroute. The other operating systems send UDP segments. Note that in Linux and macOS, it is possible to send traceroutes using echo requests, but it's not default, so B is the better answer. Okay, let's go to question 2. R1, a Cisco router, sends a traceroute to 8.8.8.8. What kind of messages should it receive in response to this traceroute? Pause the video now to think about the answer. Okay, the answer is A, destination unreachable and time exceeded, as shown in the packet capture below. All routers in the path should send time exceeded messages, and the final destination host should send destination unreachable messages. Specifically, code 3, port unreachable. Okay, let's go to question 3. Which of the following commands can be used to send a traceroute that does not resolve IP addresses to host names? Pause the video now to think about the answer. Okay, the answer is D, traceroute 8.8.8.8 numeric. This command is used in Cisco IOS to send a traceroute without attempting to resolve IP addresses to host names. This makes the traceroute command finish much faster, if you don't need the hostname information. The -D in option B can be used in Windows to do the same, but in Windows the command is traceRT, not the full word traceroute. Okay, that's all for the quiz and this video. I hope it was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Yonatan Makara, Velva Jacob, George Streeter, Funny Dart, Nasir Chowdhury, Devin Suku, Gustavo BR, Gerard Baker, Marcel Lord, Pavel M., Mr. Erlison, Dragos Hirnea, Zakib Shah, Mayor Salman, Mazen Anderson, Vitaus194, Gina Lindley, Mark Jackson, Bold1C1U, Michael Carroll, Gerald Guillaume, Gabriel Braga, Renan Marias, Hector Hernandez, Maratuba, Roji Kuriakos, Arpad Konives, 5 Feet, Owad, Daniel Brown, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, Hussein Yavuz, Samuel Tavares, Mustafa Irsoy, Dear Diso, Nasser Zahar, Brian Grant, Alexandru Badic, Georgi Gemejev, Dibya Swain, Arlen Plagaria, Adelson Pereira, Farad69, Lucian Stoichitoyu, Madmark 50484, Sean Powell, Alexandru Stratan, Hiago Bicalho, Pradeep Halder, Pyotr Kaimov, Abubakar Berry, DMJ2, Kurt Nell, and Preeti Dongave. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So, if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.